Okay, so in this video, I'm going to talk about the two-pointers technique. The two-pointers technique usually involves some array, and our goal is to find an interval on this array somewhere that satisfies some condition or optimizes some target function. Or it can be just finding maybe two numbers or a pair of numbers that satisfy some condition or are optimal for some target function. If you do this naively, so the naive approach would be to just check all pairs, and that would be and choose two pairs, and usually you can come up with a big O of n squared solution for that. With the two-pointers technique, you can bring that down most of the time to a linear algorithm, and I'm going to show you a few examples how this works, because there are multiple ways you can go about it, and I brought like one task for each of these. So the first one is the two-sum task on LeetCode. This is a pretty standard problem. So you're given an array of numbers. They are already sorted for you, so you don't have to deal with that. And you have to find two indices for which those numbers sum up to a specific target number. And then you have to return those indices. So naively, what you would do is you would write two for loops. Let's save our size to shorter variable. And they do say that the indices have to be in this certain order, so I'm gonna say that j starts from I plus 1, so they are unique, like they are not, so they are distinct indices, and they are in the correct order already for me. J is to n plus j, and then just say if ai is plus, sorry, for the numbers, it's not ai, numbers. If numbers I plus numbers j equals the target, then I'm just gonna return those indices in a vector. You can create vectors like this using an initializer list. It's pretty handy for situations like that. And I think the compiler is gonna complain, so I'm just gonna return some random value here at the end, so it doesn't say that there is no return at this path in the code. So I can run this. Oh, it's one indexed. Hold on, yeah, because they like to sometimes do that to you. Okay, so at least on the test cases, it ran and found the correct answer. However, if I actually submit this, it's gonna give me time limit exceeded. So the solution is not the naive approach. This is too much. Oops, this is too much. And that's because the constraints that we have for the problem, the numbers, so you have 3 times 10 to the power of 4 numbers, and n squared on that, and choose 2 on that, would be around 10 to the power of 8. And that's too much because like, roughly 10 to the power of 7 is 1 second on these platforms. So we are out of time with this. So instead, we should do something clever. So what we are going to do is initialize 2 pointers. I'm going to call them left and right. And I'm going to put the left pointer to the first position in the array. So it's going to point to index 0 at first, and the right pointer is going to point to index n minus 1. Let's actually make this a proper array, something like that. Okay, maybe even put some numbers in. Do we have an example? I want a bigger one. Okay, so let's say this is the array, and my target number is going to be number 13. So this is what I want the sum to be. Right now, my 2 pointers are pointing to a sum that is minus 10 plus 21, that's 11. Sum is too low. It's less than the target. What should I do? So in this scenario, I can increase the left pointer. I'm gonna step to the right bit. Why am I doing that? Because my sum is too low. I need to increase it. And the only way to increase it in this scenario is with the left pointer. So I'm going to now calculate the sum. It's gonna be -1 plus 21, which is 20. So now it's too much. It's larger than 13. I need to decrease the sum now. And the only way I can decrease it is to move the right pointer towards the left. So number 13, -1 plus 13, okay, that's 12. It's not enough, so it's too small. I'm gonna increase the left pointer. 3 plus 13, 16, that's too much. So now I'm going to decrease the right pointer. 3 plus 11, 14. It's still too much, so I'm gonna decrease the right pointer again. 3 plus 9, it's 12. Not enough. Increase the left. 4 plus 9, 13. And we are done, because we have found a solution. Left and right point to two numbers that sum up to the target number. So at least on this example, this worked. But why does this work? So how can I prove that these rules that I'm using right now are correct? So this is my rule set. When let's just call this, I don't know, array A. So this is the A array, and then this is the left and the right pointer. So when the left plus right is less than the target, then what I'm gonna do is increase the left, and it's larger than the target, and I'm gonna decrease the right, and when it's equal to the target, then I found the solution. At least that one is clear. But these ones require some reasoning on why this works. So whenever I'm in a situation, so the important part about this, so it's very important that the array is sorted, and we are going to use this fact for our proof. So whenever I'm in a situation, let's say at the beginning, so at the beginning, when I'm in a situation where the sum is too low, so it's less than a target, then I said that I'm gonna increase L. So that means I'm never gonna come back to the L pointer again. So I mean I'm never gonna come back to the first position again. So that means I have to be sure here that there is no possible solution that contains this specific position. That position has been eliminated. And why is that the case? Well, because AR is the maximum possible pair that I can give to the left pointer. So this is as big as it gets. Like, what other positions can I pair up L with? They are all here. So this means that they are less than or equal, see? Less than or equal than R. So anything else here, maybe some other option, would be worse for me, because this number is less than or equal, less than or equal than AR itself, using the fact that the array is sorted. So after seeing just this one pair's sum, I am absolutely sure that L is never going to be part of the answer. So this has been eliminated. With the exact same reasoning, if at my current location, or at my current L and R positions, if my right pointer is pointing to this place, and my left is maybe here, if the sum is too big, bigger than the target, then I am going to decrease the right pointer, and that's because if this is too much, the left pointer is pointing to something that is as small as it gets. So I cannot find anything better to pair up R with, because everything here would be bigger than the L pointer, so it would be pointing to, so it would be even bigger than the target. So there is no way I can get something that would be equal to the target. So I have eliminated this position altogether from the rest of the possible solutions. So this way what I'm doing actually is keeping track of an interval, and I'm always eliminating like the sides, so it's always decreasing in every step, and I can always be sure that the solution, if it exists, is still contained inside the interval. Everything I'm eliminating cannot possibly be the solution. And this technique is really cool, because if you think about the number of steps you are taking, well, so eventually you either find a solution somewhere, or your pointers are going to meet, like something like this. And if it turns out that even that pair is incorrect, then what you are left with is an empty interval. So if this is still not good, then there is no solution. Your pointers do not cross over, so the left pointer is always smaller, like at a smaller index than the right pointer. If they meet, you can stop the algorithm. And that means that altogether, how many steps are you making? Well, as many positions there are in the array, because that's how many steps it takes for your pointers to meet in the worst case scenario. So the time complexity for the solution is linear with of n, where n is the size of the array. So let's code this. Let's throw away this for loop, and instead let's initialize our pointers. So I'm going to point to the leftmost position in the array and the rightmost position, and -1. And I'm going to create a loop, and my condition is that my pointers are not supposed to cross over. So when they meet, or if they like move in a way that they would switch positions, then my algorithm is done. So inside here, what we do is check the sum. So if the currently pointed cells are smaller than the target, then we are going to increase the left pointer. If they are, let's put it this way, if they are larger than the target, then I'm going to decrease the right pointer. And else, that's when they are equal, I can return because I found the solution. And because this is a one indexed array, I'm not making the same mistake again, so left +1 and right +1 is going to be the solution. So I think that's it. Let's see if I got that first. Okay, so at least on the test cases, okay, let's submit it, and it's accepted. So we've solved our first exercise. Let's look at the next one. So this one is on Codeforces. This site is a bit different. They don't offer you a code editor, so I'm going to pull up VS Code for it. But other than that, it's very similar to LeetCode and how it works. So the next exercise we are going to look at is physics practical. And in this one, we have Vasya, who is probably a physics student, and he is making some measurements of something, recording the results, and he has to submit this to his professor. But the professor has already made his friend redo the whole experimentation because he found values that were too far apart from each other. So the largest and smallest one differed by more than 2 times, and that probably means that the experiment was done badly. Unfortunately, Vasya is lazy and he doesn't want to redo the whole experiment, so he's just going to remove some values so that the remaining ones just fulfill the professor's wishes. But he also doesn't want to make the teacher suspicious, so he wants to remove as few measurements as possible from the notes, help him, I guess, cheat on his exam or whatever, cheat on his laboratory. And again, n is pretty big, so an n squared solution does not fit into the bounds. And we are going to use 2 pointers for this one. The first observation, the input numbers are not sorted right now. The first observation is that we need to sort. Okay, so the first observation we can make is that we should sort the input array. Why do I want to sort it? So if I have the numbers in the sorted array, if I just pick any subset here, so let's say I'm picking these numbers. So let's say I pick a subset of numbers. So in the sorted array, they would have holes in between them, possibly. But if they have holes in between them, I could make this possible solution even better if I also included these numbers in it. Why? Because the only thing I actually have to check is the two extremes, the boundaries of the set. So this one and this one. This is like x and this is y. As long as y is not too big, as long as 2 times x is larger than or equal to y, then we are good. Because, so as long as 2 times x is larger than or equal to y, then we are good. I don't have to check any of the numbers in between them, any other pair, because these are the two extremes, so the other numbers will also be close enough to each other. So what I'm actually looking for is subinterval of the sorted array. So this whole interval will be a possible solution, and that looks like a good setup for a 2 pointers. So what I'm going to do is going to be a bit different than what we did previously. So previously we had a left and a right pointer, and I initialized them at the beginning and at the end of the array, and I just started moving them closer to each other. But in our scenario, we're going to do something different. We will have 2 pointers, both initially pointing at the beginning, but one of them will be slow and the other one will be faster. The slow pointer will just advance one by one, and the fast pointer is going to make possibly more steps, so it's going to be advancing faster, hence the name. It's going to find the best maximum, so best upper bound pair that works with this specific slow pointer position. So in the first step, my slow pointer is at index 0, and I'm gonna keep advancing my fast pointer until the condition that 2 times a slow is larger than or equal to a fast holds true. As long as this is true, I'm gonna keep moving to the right. And eventually I will find the position where the number is just too big, and that's when I'm gonna stop. So these were all okay pairs for the slow pointer, but this one is not, and I stop here. Now I know the best solution that contains or that involves like the first cell, and I'm gonna record this information. So I'm gonna say this interval, I don't know, some size, and I just keep track of that. And now I can move my slow pointer to the next position because I'm done with this cell. And what do I do with the fast pointer now? Do I have to go back? Luckily I don't, because remember that the array is sorted. So whatever I'm pointing at now, let's say slow prime, is larger than equal to a slow. So 2 times a slow prime still satisfies this condition for all of these values that we have passed with the fast pointer. I don't have to check it again. So I can keep my fast pointer at the same position and check how much further I can move with it. Possibly I can move a bit more to the right because my slow pointer is now a bit bigger. My slow value is a bit bigger. And then once I find the boundary again, I will calculate that size, and then I guess I'm just gonna keep track of the maximum size that I have seen previously. For each specific starting position, I calculate that, and at the end I have my final result. So the trick here was this inequality holding true because the array is sorted. So my fast pointer doesn't have to go back ever. It can just keep advancing to the right. So let's code this. I have my setup already here. So I copied these two inputs into my editor. So this is input number 1, this is input number 2. And these are the answers. And I just have this handy script that compiles my code and runs it for all of these input files and puts the answer into these files. So that's what I'm gonna do. So the format of the input is, first number is the number of measurements, and then you have the measurements themselves. And so we are going to read that in. And as I said, we are going to sort the measurements. And then we will do our pointers things. Since the slow pointer just steps one by one, that can be a for loop. So force of habit. And because I want to keep track of my fast pointer's value in between iterations, I'm gonna create it outside of the for loop. And the 0th number is gonna be less than or equal to 2 times itself, so just start with 1. So I'm going to check if my current value, a slow, is to 2 times a slow is gonna be an upper bound on the fast pointer at its current position, and if it is, then I'm just gonna keep advancing with my fast pointer as long as this condition holds true. And since I wanna like iterate this is actually a while loop. And once I find the first position where the fast pointer is pointing to something too big, then I can calculate the size of my interval. I go back here real quick. If I have an interval of the correct measurements, and my slow pointer is pointing here and my fast pointer is pointing outside of the interval, the size of this interval is just fast minus slow. So I want to keep track of my largest possible solution, 0, when I don't know anything, and then it's gonna be the maximum of what I've seen before, and the current solution I have in my hand. And one more thing that I forgot here is that the fast pointer shouldn't go outside of the bounds of the array, so let's keep track of that. When the last cell position is also a correct value, or also holds the condition, then I'm gonna leave the boundary of the array, but I'm not gonna index that number in the next loop, so this is fine. And what I'm gonna have to print to the output is actually not the best, as in like not the size of the interval, but how many measurements I have to remove. So the output is the minimum number of results Vasha has to remove. So that's n minus best. And hopefully that's it. I think. Let's see if I got it right this time. Okay. First try. Oh, one more thing. So this is kind of an older exercise. I didn't want to give it as homework because it's a bit annoying. But this one is back in the day when Codeforces probably worked with reading from an input file and printing to an output file. This is not the case anymore, so luckily we don't have to deal with this, but this was a very good example, so I just wanted to include it in the video. So I'm just going to quickly modify the code so it works with files actually. So I'm copying it because I even forgot how this works in C++ because nobody does this in like recent contests. You don't need to know how file streams work, but here they are. And I'm just gonna switch out all C-ins with this, and I'm gonna switch out the C-out with the off-stream. And just to check real quick, I'm just gonna make this one input.txt and actually hopefully it compiles. Yes. Oh no, I don't think. Yeah. I think I did it. Oh my god! Oops! I changed the name. Okay, I was in a different folder. So let's try this again. So now I've changed the correct input, and hopefully, yeah, gave me a correct output of 2. So I think if this changes, this should work. So if I submit this, hopefully it will be accepted. You can see everything I did previously. Nice. So it is accepted. Let's move on to the final example. So in this one, Valera has some free time. He goes to the library to read some books. Today he's got 3 minutes to read, so we know how many minutes we can read. And we have some books that we could read, and each of them we know how many minutes it would take to read that book. So Valera wants to read, for some reason, a subsequent, it's like a sub-interval of those books, and he wants to read all of those books from cover to cover. So we want a sub-interval of those books, and we want to maximize the number of books Valera can read. So what is this exercise actually translated is we want the longest interval where the sum is less than or equal to the target value. So how do we do this one? So previously we have had these left and right pointers. We also had a slow and fast one. And what we are doing right now is called the sliding window. So for this one, so I'm just going to call the pointers begin and end in this case. And what we are doing is we're always keeping track of an interval of numbers, or an interval we are always keeping track of an interval of numbers, and in each step, so we know what the current sum is for our current interval. So let's say I'm at this position, this is my begin, this is my end, and I know what the sum is for this interval. If the sum is too big, if the sum is larger than the target, now what I'm going to do is I want to decrease the sum. How do I decrease it? By moving my beginning pointer to the right one step. So I'm just gonna cut that part of my interval and move the beginning here, and I decrease my sum. So this is plus back. If my sum is smaller than the target, then I want to increase it, and for that I'm going to move my end pointer again to the right. Okay, so I'm adding this one. Very nice. To the interval, so plus end. And if it's equal, well, then we are happy because we found the solution. Or at least we have found one possible solution. So we keep track of the size, and then updates the maximum size we have found previously. And so this means that even if we find something like this, we are not returning, we just keep iterating and do the same thing again. For the equality, we are going to move both of the pointers, because if I only move one of them, then I'm immediately in a situation where it's too small or too big, so I can move both of them. So why does this work? So let's say that, so these are my rules again. Let's say that there was a solution interval somewhere in this array. So let's say, I'm going to draw a new array. Let's say that we have an array for which the sum is exactly the target. So what's going to happen as I'm doing this sliding window technique is eventually the beginning pointer is going to point to the beginning of this possible solution, since we are increasing it one step at a time, so it's gonna move all across the array. Where can be the end pointer in this scenario? So where did I come from? Is it possible that the end pointer is already here, after my happy array? So this is my happy array. Is it possible that my end pointer has already gone past this happy array? The answer is no. And the reason is, how could the end pointer come to this position before the beginning pointer was at some previous location? The only way the end pointer can move here is if the current sum of my current interval was too small. So this is the second rule that we have here. So this is the rule for advancing the end pointer. That means that whatever was between the beginning and the end is too small. But that cannot be the case. And in this scenario, it's important that we don't have any negative numbers. So no negative numbers. So previously we needed the array to be sorted. In this task, this exercise, we need to have no negative numbers that could possibly drop the sum. If I had some big number, yeah, so in this case, we need no negative numbers. I want to know that if an interval contains a correct solution, then its sum is gonna be greater than or equal to the target number. So there is no way we ended up here, because the only way to do that is via this rule. But the fact that we have a solution inside this interval violates that the condition for this rule. So the end pointer, while the beginning pointer is before the beginning of my happy array, happy interval, the end pointer has to be somewhere. It's gonna be a lot. The end pointer has to be somewhere here. It has to be between the beginning and possibly even like here or something, but details. So if the end pointer is there, that means that once my beginning pointer is here, my end pointer is somewhere not further away than my target. And then, since this sum is less than the target, again, because no negative numbers exist in the array, I know for a fact that I'm going to keep increasing my end pointer because of the same rule here until the target equals the sum equals to the targets. So if there is a happy interval inside, these rule sets make it so that eventually I will have the beginning pointer pointing right at the beginning, and eventually the end pointer will find the ending of that happy array, and then I will have that as one possible solution. And I can keep iterating again. So this rule, so the third rule, the reasoning why the third rule is correct is because it's actually a combination of two rules. The first step is saying that once I have the correct ending for this beginning position, that's the only answer with that beginning position. So no other possible endings could work, because I think we don't even have zeros in the array, so it cannot be that the sum equals again to this same target later on. So I can increase my beginning pointer, and immediately after that, because there are no zeros in the array, we know that the sum will be less than the target, because I just removed one number from a happy interval, so I can also increase the end, because that's what the rule says for when the sum is less than the target. So this rule set guarantees that we will find a solution eventually. I didn't talk about the first rule, but so you have to make a similar argument for the first rule that I guess you have to make a similar argument for the first rule that when the ending pointer reaches an end of a happy array, then my beginning pointer cannot be already inside that array, because then that would mean that it was advanced because of the fact that the sum was larger than the target, but this sum cannot be larger than the target because it's part of the happy array. So this rule will not be executed when the end is here. So this rule will not advance the beginning pointer into a happy interval when I'm already standing at the ending position of it. So it's like symmetric. You get the idea. And of course, none of these reasonings have to be this detailed when you are actually writing a contest. You just have to intuitively know how this works, and then as long as, I guess on ICPC, as long as your teammates believe you and understand what you're saying, then you just code it and submit it. Small modification. So actually the exercise is asking for, because like you have like a target sum, but you don't have to read for exactly that many minutes. You only have to be under this limit. So easiest way to do this is to just merge the second and the third rule. I think the reasoning is very similar, and it's still good that you know how to find an equal like subinterval that are equal to the target. But in this scenario, I'm merging these two rows just into one. And all of these are going to be happy arrays because they are under the limit. And I'm just gonna advance the end because that's like part of this rule anyway. And the beginning is like gonna be in the next step because the next rule will decide if the sum is like too much or not, and then the beginning will get advanced or the end will get advanced. So it's even simpler this way. Yeah. So this is happy array, this is sad array. We don't like sad arrays. Okay, so let's go with it. Vector int. It's good practice to keep in mind the sizing limits because sometimes they don't fit into long, so that's why I keep checking. N is 10 to the 5. 10 to the 9 fits into an integer because integer usually is 32 bits and it's signed. So what that means is that you have the 0 here, which is actually part of the positive range for the integer. So I have like some x value here and we have like one more here. So this is x plus 1 values in the positive range and x plus 1 values in the negative range. Mathematically 0 is neither positive nor negative, but in IT it is positive. And so what this means is, so total we have 2 to the power of 32 possible values for integers, but it's gonna be halved because one side is a negative, and then because 0 is here we actually have like -1 on the positive side. So this number, this 2 to the power of 31 minus 1 is the maximum number you can store in an integer, which is around 31, which is around this. And what you have to remember about this is that this is sort of 9 places. So 2 times 10 to the power of 9 is around the upper limit of the integer range. And actually, if we are here already, then similar argument, but for a 64-bit number, which is long, 2 to the power of 64, 63 actually, 63 minus 1, Wikipedia please. Yeah, so 9 times 10 to the power of 18. Yeah, so these are your limits. So what I remember is just 10 to the power of 18 and 2 times 10 to the power of 9, because the way they set tasks is you need that 2 times thing in it. But right now we don't have to worry about that. So we are within the limits. It's always good to check. Okay, sliding window. So I want beginning pointer and the end. It's not a pointer, it's just an index, but I keep calling it pointer. And I want to keep track of the current sum. The current sum, what's the sum inside the interval, is gonna be right now just a0. And what I want to do is to do a while loop, while we are not outside of the range. I might modify this later on, but let's just use that first. While I'm not outside of the range, I want to check my condition if the current sum that I have is less than the target. So if it's less than or equal to the target, then we are in a happy interval right now. So I want like max size to be updated with the current length of my interval, because this is left and right inclusive. There is a +1. So previously we had fast minus slow because fast was outside of the interval. If it's left right inclusive, we have n minus b inclusive. And in the hold on, because I also have to advance my pointer. So in this scenario, because my sum is small enough, at least currently, I can advance my end pointer. In this case, I can make it even, try to make it bigger if I can. If I turn it into a sad interval, then it will get taken care of in the next step. So I'm advancing my end pointer, and also I'm going to add this to the sum, and I'm just going to do it in one line because The problem is that I could go out of bounds of the array. Sometimes when you're lazy, you just do things like this. Put a 0 there. That means that it's like I think they call this like sentinel. So it's an extra value for you, just so you don't run out of the bounds, and you don't have to write like more complicated code to check for running out of the bounds. So I put a 0 there. I made the array like one size larger, and in this way I can just do this with my sum. Because I advance the pointer, and if I happen to be outside of the original range, I still have that 0, but that doesn't get added to the sum, and then the while loop is gonna terminate after anyways. So hopefully this will work. And then the other scenario, we have sum minus equal a plus begin, and possibly due to the same argument, the begin pointer is also safe, but the way this whole thing works, the begin pointer will be like maximum equal to the end. So it's not gonna like go over it, because when the sum is 0, it's definitely less than the target. So it's not gonna run into the end pointer. So I think this should be the code. We'll see. And what that means is that I could probably just have this as the condition, because I don't need to worry about the beginning pointer. But I'm gonna leave it there right now. And I believe this is it. This one max up. Let's see. Well, before I run it, I like to commit the actual correct inputs and outputs, because then when I calculate the new ones, I can just see the difference. And it's not good. Okay, so for this first input, I think the size is only 2, but it's actually 3, because I can read these. So what did I mess up? So again, I look at it a little bit, just try to read the code, see if I can find the error, but if I fail, then I start debugging. That's easier. Just looking at the codes, I just made this extra thing here, that's fine. My sum, left inclusive, right inclusive, so sum is just the first element. Max size, okay, starting out with 0 if the sum is less than or equal to t, target. Then that's a happy interval, so I can check that size, and then, or I mean I can keep track of that size. And minus begin plus 1. It should be this way, because it's inclusive. That's one of the things that it likely goes wrong, because I just have a 1 difference, although I don't have a difference for the other one. Yeah, because this is just okay. So increase my end pointer. This one is good. I got these. Let's get back to reading it in. Okay, so put a breakpoint there. Okay, so I can see my variables here right now. Okay, 0, 0, sum is 3. Let's go. So I'm gonna keep track of this value, because yeah, size is 1. Nice. And I'm gonna increase my end pointer and the sum as well. So right now I believe that the sum is 4, which should be correct. Beginning and end pointers are like that. And I can increase again. And now my sum is 6. Beginning is 0 and this 2. This is 6. So this should be the time when I'm, oh, haha, see what I messed up. I'm not decreasing the sum by the new beginning one. I'm decreasing the sum by the beginning one that was previously the value. Like I'm moving off of that position. Okay, we'll just fix everything. Nice. Let's submit this. You can see my previous efforts. So running on test 9, yeah, it's accepted. Okay, we are done. Nice. So I hope this was informative on how you can do 2 pointers. We have some homework exercises again, which will be posted in Discord threads once this video is released. 3 sum is very similar to the 2 sum problem, but now you have to find 3 indices that sum up to a specific value, which is 0 always, and they have to be distinct indices. So that's the first one. I believe this is this is an exercise that, so I checked, like I was trying to find multiple possible exercises to give, and I specifically checked that it will not accept a naive solution. I didn't talk about this, but it would be a good time to talk about this now. In many cases, problems that can be solved with 2-pointers can be also solved with binary search. So there is like this overlap. So just thinking back on the twosome problem, another thing you could do, if the twosome problem was given to you in a way where the array is not sorted, then you would have to sort it first. It would be n log n. And in this scenario, even though the 2-pointer technique ends up being linear, the sorting part makes the whole algorithm n log n. And in this scenario, another thing you could do after sorting is to just do a linear search. Just iterate on the positions. And then if you know that the value is x here and you want the sum to be t, then you know that you are looking for the value t minus x somewhere in this array, which is already sorted, so you can binary search for all positions. That you learn this in theory of algorithms too. And actually I remember that someone in my practice session did say 2-pointers as an alternative solution for this. So it's one of the things that overlaps. Physics practical, again, you could do this with binary search as well, because you're looking for the first value that's too big, or the first value that's or the smallest value that's bigger than something. That's also a binary search. The books one is not an overlap. The problem here is that even though, so if I'm like doing a binary search for the end pointer, yeah, I'm wrong. So I wanted to say that if I'm doing a binary search for the end pointer, I still need to like sum up all of the values here, but I could just use like a prefix array and then like prefix sum them, and I could find the sum in constant time for an interval. So this also is something that could be done with a binary search. But for the homework problem one, I even tried the binary search solution, and it was time limit. So that's one. So this one doesn't even accept a binary search solution, because you have 3 numbers, so you can linear search the first 2, and then the third one you could binary search. But they cut that off from like the accepted solution, the accepted time limits. Because how they set these problems is they write like example solutions, usually using multiple techniques, and they put the time limit in a way so that it divides the solutions they don't want to accept and the solutions they want to accept. So they know exactly where to put that time limit. So they are only accepting the solutions that are theoretically a certain big O, a small enough big O, which is really cool, because you can just test for this in practice, not just by proving time complexity. Okay, so this is the first one. We have a subarray product less than k, so you are looking for like subarray, multiply all the numbers in between, and find a continuous subinterval where the product of the elements is strictly less than k. Another one. Then we have container with most water, which is you have these vertical lines, I guess. They all have different heights. I mean, okay, so they can have like same height, but okay, so they all have some height, and you wanna pick 2 vertical lines so that the water this tank could hold, which consists of the 2 lines themselves, and the width of the tank would be the distance between those 2 lines on the x-axis. So they are like at integer coordinates. What is the area of this rectangle, basically? And you want to maximize this area, so you want to maximize how much water it can hold. And, between the 2 borders, the smaller one determines the amount of water that can fill this tank. This is a bit harder than the other ones, so you need some consideration on how or on why the solution is correct, or how to like prove that this solution is correct, but it's also similar to pointer exercise. And then we have for the challenge Vasya and arrays. Now you have 2 arrays, so this is why it's a challenge a bit. And in each arrays you have like some numbers, and you can do an operation of taking consecutive subsegments, subinterval of one of the arrays, and replacing it with the sum, like a single element, which is the sum of the selected array. And the task is to make the arrays exactly the same, the 2 input arrays that you have, and keep them as long as possible. And you have to output the maximum length that is achievable. So for example, in this first input, what's gonna happen is you wanna sum, so you have to sum, I guess, these numbers and these 2 numbers, and then it's gonna be 10 like in both arrays, and that's why the length is 3. So 11, 10, and 7 will be the array. And similar. And if you cannot make them equal, because sometimes it's just not possible, like in this input, then you have to print a -1. Okay, so that's it. I hope this was informative, and see you next week as well.